Hello again and welcome back to continue chapter 1, which is energy. In this part of the chapter, we're going to focus on the kinetic energy theorem, the power of a force or the power released by applying some work. Then we're going to solve some applications, and finally we'll end up the session and the chapter by a quick summary about the whole ideas that we have covered. Starting with the kinetic energy theorem, which states that the variation of kinetic energy of a system along a certain path from A to B equals the net work of all the external forces acting on that system. If you translate that to a mathematical equation, we get the following. Delta KE from A to B equals summation of work of F external. Before I move on, it's important here that when you want to use this equation as a mathematical application, that you mention the forces acting on the system in the first place, definitely after isolating and specifying the system you are going to study. Now, physically speaking and conceptually, if you just notice that equation, variation of kinetic energy equals the sum of work acting on the object. If the sum of work of the forces is positive, that means we are adding work to the system. Hence, kinetic energy increases, which is logical, right? If the sum of work that we add on the system due to forces acting on the system, in fact, is negative, that means that the overall effect is resistive and the system is gonna lose kinetic energy. Consequently, kinetic energy decreases. And if the sum of forces is zero and the sum of work of these forces is also zero, then kinetic energy remains constant and it does not change. Going to an application so that we just understand what we have done. We have here a skier of mass 80 kilograms moving down from O to A, as you can see on the figure, at constant speed. So from O to A, there is no change in speed. If you recall what we have seen in the previous slide, that means that kinetic energy doesn't change. Sum of work of F external is going to be zero. Anyway, we'll discuss that while solving. Where V is 30 meters per second along the line of greatest slope of a track inclined by an angle of 30 degrees with the horizontal. The track exerts on the skier a constant force of friction, F equals to minus F. The motion of the skier is represented by the motion of its center of mass, so that we ignore the dimensions of the skier himself or themselves, as shown in the figure. Neglect a resistance on the skier so far. Take the horizontal plane passing through B as a GPE reference, or in other words, a reference of height. Use G equals 10. Applying the kinetic energy theorem, or simply the KET, determine the value of the frictional force. The skier, upon reaching A, starts exerting a constant braking force to stop at B. We'll come to part 2 later. Solving part 1, in which we have the skier moving from O to A. First step is list the forces. External forces acting on the skier are the normal, friction, and weight. It's always nice to start by this order. List the forces in the first place. Now, we specify along which path would the kinetic energy theorem be applied. Over here, get along path O to A. So we specified the path where we're going to apply it. Delta K equals summation of work. It's obligatory. It's trivial to just write the equation as it is. Then we apply that equation accordingly. Kinetic energy final, which is at A, minus kinetic energy initial, which is at O, equals work of the normal plus work of friction plus work of weight, according to the list that we have done about the forces. Now, kinetic energy at O and at A, kinetic energies in fact are equal because it's given that the skier moves at constant speed. Hence, kinetic energy A minus kinetic energy at O is zero. Work of the normal, I can slash it here, is zero because it's always like that. It's always perpendicular to the path. So we're left with work of weight and work of the friction. Work of friction is minus F times the distance. Okay. Work of the weight is mg height initial minus height final. The initial height is at O, the final height is at A. We notice that we have OA is unknown. Okay. We also have friction, which we need to calculate. We have the heights at O and A, which are also unknown. But we know from previous applications and solving and problem solving that the difference in heights can always be related to the distance. How is that? If we go to this triangle here, I'm gonna change color and go to the figure. If I go to this figure here, okay, the difference in height, this is height A and this is height at O, right? This is the difference in height, which if I draw this triangle here, okay, this height, let's call it H, equals OA sine alpha. Why is that? Because in this triangle, this angle alpha equals this angle because they are corresponding angles between two parallel lines, right? And sine alpha, as we know it, equals opposite over the hypotenuse, which is here H over OA. Then we have H equals OA sine alpha. Okay, excuse my handwriting for now. Okay, thus we replace height O minus height A by OA sine alpha, replacing that in the equation minus F times blah blah blah. Okay, so in a simple step, I've taken OA as common factor here. We're left with minus F plus 80, the mass, G10. OA is taken common, and sine alpha is sine 30, which is half. And by simple calculations, F is gonna be 400. So that seals the first part. Now moving to the second part. In the second part, the skier applies brakes to stop from A to B. Again, we are supposed to determine or to verify that the distance from A to B, sorry, is 45 meters. So we're going to use the ket. First thing we do is specify along which path are we going to apply it and list the forces acting. That was done in one phrase. Along path AB, we specified the path. Forces acting on S, external forces acting on S are, it's the normal reaction, friction, the weight, and force F1, the braking force. And you notice that we directly drew these on the figure. Now, applying the ket, delta K equals work. Delta is final minus initial, so we just replaced this by KE at B minus KE at A, final minus initial, listing the forces and the work of these forces. Definitely, work of the normal is 0. We have an additional 0 here, which is the work or the kinetic energy at B, because it stops. The skier stops at B, thus kinetic energy at B is 0. Hence, we can replace in the equation. Notice, let's switch color. Okay, 0 minus half mva squared equals 0 minus this. Now we notice that we have a lot of parameters that we already have. Half mva squared, that's trivial. F times AB, okay, AB is what we need to find. Mg is 800. Height A minus height B, using the same manner that we have done before when we have used the triangle thing. This is B and this is A. If I just want to find the height of A, because height of B is 0, right? This is the height of A. If this angle is alpha, height A is nothing but AB sine alpha, and here it is. Minus F1, which is given to be 800 times AB. Now, replacing values and isolating. Minus 80 times 900 is minus 36,000, minus 400 AB plus. Notice that these cancel out. This was, by the way, expected. Why? Because in part one, we had V equal constant. So mg sine alpha equals the friction. I'm just mentioning this because those of you who would like to use concepts like ideas without using mathematics could have directly eliminated that in the first place. AB equals 36,000 over 800, which is simply 45 meters. This seals it concerning this application. Okay, I went over it quickly. You can check it and read it or listen to the video in details and try to solve it on your own so that you get acquainted with the methods and the strategy to solve problems using kinetic energy theory. Now we have reached the last part of the chapter, which is power of a force. Before I move on, it's important to mention that when we say power of a force, we mean by that over here in this chapter and on this level of studying, we study the power of a constant force. What we're going to discuss is applied for any force, even if the force were not constant. But for the time being, don't think about it because we do not need to focus on it. So what is power? Power is the rate of energy per time. Mathematically speaking, power in watts is energy per delta t duration. In mechanics, other than relating power to energy in general, we can also relate it to work, and thus we call it mechanical power. So that's what we call mechanical power. And what does the equation become? Simply, if we replace energy or instead of writing energy, we write work, we get average power is work of the force over delta T. Delta T because we are talking about average power. Regardless of whether the work changes or anything, when you calculate the total work divided by the overall duration, we get the average power in watts. And if we specify at a certain instant, then instead of saying delta t, we use dt, then power instantaneous Pi becomes d work by dt, standing for infinitesimal variation. Now, d work is f dl or dx. Here we can either say f dot dx or f dot dl. Notice that I've written the vectors because this is the general idea, which is nothing but f dot v. If f and v are collinear and in the same sense, power is going to be positive. If f and v are opposite, then we have negative power. So yes, power can either be motive, positive, or negative, resistive. This is just an idea that we already know from work, and it's nice to just remind ourselves about it when we discuss power. Now, focusing on this idea and the fact of having average power and instantaneous power, we will go check an application which also focuses on the graphical interpretation of power. Application 7. The adjacent figure shows the graph of the variation of mechanical energy of a system relative to time. Now, the overall duration is 20 seconds. And notice we are talking about energy with respect to time. That energy is mechanical. First question is to determine graphically the instantaneous power on or off the system at time equals to 4 seconds. Why on or off the system? Because you might consider this as how much power is added on the system or how much power was done by the system. Regardless of what caused that power, how would you calculate it? The question determines that we need to work or asks us to determine graphically the instantaneous power. So to answer that, let's move on. So part 1, determine graphically the instantaneous power on or of the system at time equal to 4. Instantaneous power is the power at that instant. Mathematically speaking, we can simply say it is dE by dt. Why E not work? Because the graph here shows E. Now we know that dE by dt is from one side variation and from the other side it's also slope of tangent, right? The good thing is that the graph here shows that tangent. Instantaneous power is given by dE by dt at this time or this instant. So P at 4 equals dE by dt at time equal to 4, which is the slope of the tangent at that instant. How would you find slope? We know that slope is rise over run. What is the rise here? The rise is moving from here up to here, which is this. So here is the rise. And where is the run? It is simply running from 0 to 4. This is the run. So slope is rise over run, which is 26.5 minus 17.5 over 4. Now, units are joules and seconds. So this is joule per second, which is nothing but the watt itself. Okay, so here it's better to say rise instead of raise, but it's fine. Okay. The second part is to determine the average power. We know that the average power is simply the rate of consumption or change of energy or work over the overall duration. So notice here that the variation of energy is not linear. So how would you do that? Simply go to the definition, which is the overall change, from this point up to this point. And all we have to do is this point because we have here time 20, right? So delta E is 35, the last point, minus 0 over 20 minus 0, which is 1.75 watts. You notice that there is some difference, and that's logical because the power will keep on changing instantly because the slope of the tangent will keep on changing. That's it concerning this application. Now, we have come to the end of the chapter in which we sum up everything we have seen. So first, the work of a constant force is given by this equation, FAB times cosine. Work of weight is worth memorizing, in which we have mg height, A minus height B. Calculating height, if you look at the right-hand side, we have two important methods which we can use. One which can be used with inclined planes, this one, and this one which we can use with circular motion or when we have circular trajectories. Work of friction is minus F times the path that we follow. Okay, work of normal is 0, but that's easy. Power, which we have covered at the end, I added it here so that things which are related to each other remain close to each other. Power is energy or work over time. We have instantaneous power, which is d work by dt, which is F dot V, or slope of tangent, in case you have it. Average power is work of the force in general over delta T. Power in mechanics is referred to as mechanical power. Continue with that. We move to energy. Energy is macroscopic, which is mechanical, and microscopic, which is internal. Macroscopic energy is kinetic and potential. Potential can either be gravitational or elastic. You are given the equation. We might have some other forms, but beyond the scope of our level and this chapter. The microscopic energy is internal energy, which is also kinetic or potential. But we will not go into the details of what sorts of kinetic. We might have translation and rotation. We will not go into potential because we have nuclear potential, electric potentials. We can have different types of potential energies, but they are beyond the scope of this chapter. Now, mechanical energy can either be conserved or not conserved. If it were conserved, first, when there are no non-conservative forces, in particular friction and traction, keep that in mind. When it's not conserved, sorry, when it is conserved, we use delta ME equals to 0. We can also use mechanical energy initial equal mechanical energy final. We can use, let me erase this, okay, we can use mechanical energy equals mechanical energy final. We can use variation of potential is opposite to the variation of kinetic, and we can use that derivative of mechanical energy with respect to time is 0. This is not very important now, but later on when you go more and more into the mathematics of solving physics problems, you will find this extremely handy. On the other hand, when mechanical energy is not conserved, first, it is not conserved when we have non-conserved forces such as friction and traction. We might have some other things. If you remember in the chapter, we mentioned something about chemical energies and stuff like that. This is just a summary here. When it's not conserved, we say delta ME equals work of non-conserved forces. The derivative of mechanical energy equals the power of non-conserved force. This is not very important when you are studying this chapter. Okay? Now, ending everything, we have here an exercise which is an overall summary about all the ideas that we have covered. It involves power, it involves kinetic energy theorem, and it involves some calculations of energy if needed. Okay? Solve this, and if you are using the CRDP national book, you can go to page 24 or 25, I think, but it's not evident here, and try to solve exercises 16, 17, and 19. In upcoming videos, we're going to discuss in more details the solutions of all these problems. We have reached the end of the session and the end of this chapter. the chapter where we have covered almost everything about energy, mechanical energy, conservation laws of mechanical energy, and the work energy theorem. Now, before we leave, today's idea is about hydroelectric energy, in which water is trapped behind a dam, then driven to produce waterfalls, where potential energy of water is converted to kinetic energy at the bottom. Then at the bottom we add a turbine which takes this kinetic energy of water and converts it by rotation into electricity. This is a very promising and non-polluting method of electricity production. If you're interested, you can go to Google and search about it. You will find tons and tons of articles covering it. Thank you for your time. Stay safe and take deep care of yourselves.